Hello, let me first introduce myself. My name is Yeonuk Jung, taking classical mechanics course taught by Professor Myung-soo Kang. This is a talk for my 15-minute video project. My topic is Liouville integrability. As we learned in classical mechanics, we focus on exactly solvable systems. From the historical perspective, finding and solving exactly solvable systems were major goals of Newtonian mechanics, formulated in late 17th century. The chief example of exactly solvable system was the Kepler's problem, yielding a multitude of successful predictions in celestial mechanics. In 19th century, Joseph Liouville introduced the notion of integrability, which means that the system exhibits regular dynamics, not chaotic dynamics. One must note that integrability and solvability does not imply one another. For example, there are exactly solvable chaotic systems and dissipative systems that are not integrable. This includes the simple case of motion of a box under friction, where no regular motion takes place but exact solution is known. On the other hand, there are cases like thermodynamic Bathan thoughts, which is integrable but only yields numerical solutions computationally. Despite this, integrability, due to its nature, has caused enormous amount of deep and general underlying mathematical structure, where several mathematical developments took place in the 20th century. From now on, I will present some of the basic concepts in classical integrability. To begin with, let me shift the Hamiltonian mechanics onto more rigorous mathematical notations. The phase space is formally considered as the symplectic manifold, which consists of a smooth manifold and a symplectic form. On the symplectic manifold, we have the canonical transformation of the canonical coordinates given by a point on the symplectic manifold and its cotangent bundle as momentum, which preserves the symplectic form, more familiarly known as the symplectic condition, preserving the symplectic matrix. These respect the Hamilton's equation, which we desire to solve. The mathematical language on symplectic manifold is differential geometry, where we have the exterior derivative and wedge product as the elementary operations. Exterior derivative, by definition, is zero when applied twice, and the wedge product appears in the result of applying the exterior derivative, which is antisymmetric. For example, we have the canonical 1 form alpha, which becomes the canonical 2 form omega. Here, the derivative results only on the first term, since the second term gets d squared, which vanishes. We can rewrite it reversing the order with the minus sign. The canonical 2 form is used as the canonical symplectic form. We also have the dual operation of exterior derivative, the integration which we can integrate over differential forms. We can rewrite the Stokes theorem, which shows the path independence property. With these more formal language, we define the most fundamental notion of integrability, which is introduced by Liouville. It is well known that for 2n-dimensional symplectic manifold, there exists at most n conserved quantities. With this, we define the Liouville integrability. If a system has maximal n quantities, which are conserved and involutory, meaning that their mutual Poisson brackets vanish, we call them Liouville integrable. Note that since we have the maximum n conserved quantities, the Poisson brackets with h vanish, meaning that h is a function of f mu. But why do we care about Liouville integrability in the first place? It is because of the following theorem by Liouville and Arnold. The equation of motion of a Liouville integrable system is given by direct integration. The proof is simple and insightful. Take a submanifold MF, which is constrained by the conserved quantities. Take alpha and omega as the canonical 1 and 2 forms. Within MF, we define the quantity denoted by S as an integral of alpha over arbitrary curves starting from Q0. This is a function of f mu and q because it is path independent, which comes from the Stokes theorem. Let's apply the exterior derivative to S. Since it's a function of mu and q, we can expand it in terms of dq mu and df mu, where we define the new quantity partial s partial f mu as psi mu. If we apply the derivative once more, we get 0, and we can identify the first term with the canonical two form or the canonical symplectic form, and we conclude that it can be rewritten in terms of f mu and psi mu. Thus, there is a canonical transformation which preserves the symplectic form, and hence we can write down the Hamilton's equations. This is the power of Liouville-Arnold theorem. The Hamilton's equations are constant, and we can now integrate this over time, yielding a linear expression of t. However, the story has just begun. How can we determine if a system is Liouville integrable? In other words, how can we find maximal conserved quantities that are involutory? In the next page, we focus on the first condition, finding the conserved quantities using algebraic method. We define the Lux pair as a pair of matrices L and M which satisfy the Lux equation, and this should correspond with the Hamilton's equation. Then for each natural number n, we define On as the trace of L to the power of n, which is a sum over eigenvalues of matrix L, power of n. Then let us examine the time derivative of this On. By the product rule, we have the sum of traces, where by definition of Lux equation we substitute the commutator of M and L. Expanding this commutator and using the cyclicity of trace, we find that this corresponds to 0. This means that the eigenvalues of L of the Lux pair are conserved quantities. I want to make a remark that there is a gauge freedom for the Lux pair, where if we transform them by conjugation with an invertible matrix, the Lux equation is still satisfied. So we are determining the Lux pair up to this gauge transformation. Now let us consider the 1D simple harmonic oscillator. The Hamiltonian is given as the following, as well as the Hamilton's equations. We can find the Lux pairs as given by the followings, expressible in terms of the Pauli matrices. The commutator of M and L using Pauli matrices yields L dot, which is precisely the Lux equation. Hence, the eigenvalue of L, which is H, is conserved quantity. This reflects more general structure that Lux pairs satisfy the matrix algebra of some Lie group G. In this case, we have the Lie algebra SU2, which is isomorphic to SL2C. Now we must consider the involutory condition. In other words, how can we check that the eigenvalues of L vanish under Poisson brackets? To answer this, we consider the tensor product space of the matrix algebra, where I use subscripts to denote each space 1 and 2. Then there is a theorem that states the following. The eigenvalues of L are involutory if and only if there exists an element R12 in the tensor product space, such that the Poisson bracket of L matrices are given in terms of the difference of the commutators with respect to the R12. For the proof, I direct you to the following reference as it is out of the scope of this talk. Note that by definition of the Poisson bracket, Jacobi identity must hold, meaning that this term and its cyclic terms should add up to 0. If you're given that R is antisymmetric, then the sufficient condition simplifies as the following. Such R satisfying this relation is called the constant classical R matrix, or R matrix, and the corresponding equation is called classical Yang-Baxter equation. Let me give you an example. There is the trivial constant solution, which is given in terms of the Bourov algebra of SL2. More interesting non-trivial solution is the R matrix of the 1D harmonic oscillator. So we can actually see that the harmonic oscillator have R matrix, which guarantees the involatility. In short, we have the following storyline. We find the Lux pairs with classical R matrices following or satisfying the classical Yang-Baxter equation. Then the system is Liouville integrable, meaning that its equation of motion is the trivial integration. For systems of higher degrees of freedom and higher dimensions, one encounters the spectral parameter usually denoted as U. For instance, I'll give you the Lux pair, which is written in terms of chi mu taking two three-dimensional vectors and m0, which takes the vector to the potential. Solving the Lox equation, we note that there is the free parameter u, the spectral parameter. And since we do not expect u to appear in our solution, we take the Laurent expansion of u, and then we can identify the equations of motion from there. We note that this is the equation for the Kepler's problem. Together with these tools, many integrable classical systems have been studied. One of them are tops, which spins with respect to the fixed axis. While most of them are not integrable, there are three famous cases that are integrable, which are Euler top, Lagrange top, and Kovalevskaya top. Now we consider possible generalizations of this algebraic method. In particular, we consider the generalization of Lox pair to field theory. We can define the Lox pair with the additional spatial differentiation, which the Lox equation should recast the corresponding Euler-Lagrange equation for the system. Such theories with this Lox pair is called classically integrable field theories. We define the monodramy matrix as an integral of exponential of L, where P is the path ordering, putting smaller variables to the right, similar to the time ordering T in QFT. Then we define the transfer matrix as small t, which is just the trace of the monodramy matrix. Again, using the Taylor expansion for the spectral parameter, we can identify the coefficient terms as the conserved quantities. It is easy to show that these are indeed conserved over time. There are several significant examples of classically integrable field theories, and they are the KdV equation, sine-Gordon equation, and the nonlinear Schrödinger equation. Their Lox pair can be exactly written down and analyzed accordingly, although I would not have time to further analyze them independently. The previous examples were significant for many reasons, but one of them was that because it gave rise to the idea of solitons, which are constantly propagating localized wave solutions, which exist for any given initial conditions. The soliton is one of the areas of active research inside the integrable systems, both from mathematicians and physicists. This idea is far-reaching in many senses, and I can give you one example. General relativity is also a field theory, but on spacetime itself with Einstein equation of field equation for the spacetime metric. We know that the Schwarzschild metric and Kerr metric for the black holes can be recasted as soliton solutions of GR. There are other active fields of research. One of them is quantum groups, where by quantizing the classical integrability notion, one finds the problem of classifying the solutions of the quantum Yang-Baxter equation. We also have applications to quantum field theory and furthermore string theory, where there are active and concrete examples like n=2 and n=4 Schuper-Yang-Mills theory and ADS-CFT correspondence. In mathematics, integrability lies in the domain of algebraic geometry and differential geometry, where several interesting theories have been developing, including the Hitchin systems. Like this, integrability, first studied by Liouville, has far-reaching implications and gave birth to a strong and fruitful field of mathematics and mathematical physics, as well as physics. I would be more than interested to be able to pursue these concepts, particularly related to my field of QFT and strings, and I hope many of you might find the same inspiration too. I have read and learned a lot from the following references, which I leave below for future reference. Thank you.